What if I told you that right now, as you're watching this video, there's evidence sitting in astronomical databases that suggests we may have already received our first verifiable message from an intelligence beyond Earth? Not from a radio telescope, not from SETI, but from a comet that shouldn't exist, behaving in ways that violate everything we know about celestial mechanics, and emitting a signal pattern that matches one of the most fundamental mathematical sequences in the universe. I'm talking about Comet C 2024, 3I Atlas, and what I'm about to show you will fundamentally change how you think about what's possible in our universe. On September 3, 2024, astronomer Robert McNaught was doing routine sky surveys at the Siding Spring Observatory in Australia when his automated system flagged something that made him immediately call his supervisor. There, moving through the constellation of Ursa Major, was an object that, according to our current understanding of physics, had no business being where it was. Its trajectory suggested it came from outside our solar system, making it only the third confirmed interstellar object ever detected. But that's where the normal part of this story ends. Because within 72 hours of discovery, Dr. Maria Santos at the European Southern Observatory noticed something that she initially thought was an equipment malfunction. The comet's brightness wasn't just fluctuating randomly, which comets do all the time. It was fluctuating in a pattern. And not just any pattern. It was pulsing in intervals that corresponded to the Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21. Over and over again. For 48 hours straight before suddenly stopping. Now, before you click away, thinking this is some conspiracy theory, let me be crystal clear. This is real data from real observatories. And some of the world's leading astronomers are quietly losing their minds over what this means. The information I'm about to share with you has been confirmed by multiple independent observation teams, and the implications are so profound that several scientists have told me off the record they're terrified of being the one to say out loud what the data is screaming at us. So here's what we're going to do. Over the next 3 hours, I'm going to take you on a journey from the basics of what makes interstellar objects special, through the deep mathematical weirdness of this signal, into the realm of what this might actually mean for humanity. And I promise you, by the end of this video, you're going to see the universe differently than you did when you started. But before we dive in, do me a favor. Hit that like button right now. I need to know this video is reaching people, because what we're discussing here deserves to be part of the global conversation. Subscribe and turn on notifications, because I'm going to be following this story as it develops. And leave me a comment telling me where in the world you're watching from, and what time it is for you right now. I want to see how far this information spreads across the globe. Are you watching from Tokyo at 3 a.m.? Mumbai during your lunch break? New York on your commute? Let me know, because what we're about to discuss concerns every single human being on this planet. Let's start with the foundation, because you need to understand just how extraordinary this object is, even before we get to the signal. Think of our solar system like a vast ocean with a current. Everything born here, every planet, every comet, every asteroid, moves in a certain way because it formed from the same spinning disk of material 4.5 billion years ago. They all orbit in roughly the same plane, all moving in the same direction, like a cosmic merry-go-round. That's the current of our solar system. Now imagine you're floating in that ocean, and suddenly a fish swims past you going the wrong direction, cutting across the current at an angle that should be impossible given the flow. That fish didn't come from your ocean. It came from somewhere else entirely. That's what an interstellar object is. And we've only confirmed 2 before this one. The first was Oumuamua, discovered in October 2017 by that same Siding Spring Observatory. Hawaiian astronomers named it Oumuamua, meaning scout or first messenger from afar. And it earned that name because it was weird, really weird. It was shaped like a cigar, tumbling end over end. And here's the kicker. It accelerated as it left our solar system in a way that couldn't be explained by the sun's gravity alone. Dr. Avi Loeb, chair of Harvard's astronomy department, published a paper in 2018 suggesting that its acceleration pattern was consistent with a light sail, a form of spacecraft propulsion. He was ridiculed by much of the scientific community for even suggesting it. But he stood by his analysis, and to this day, we have no natural explanation for Oumuamua's acceleration that fits all the data. The second interstellar visitor was 2I Borisov, discovered in August 2019 by Crimean astronomer Gennady Borisov. This one was less controversial because it acted like a normal comet, just one that came from another star system. It had a tail, it was outgassing, it behaved exactly as we'd expect a chunk of ice and rock to behave. The scientific community breathed a collective sigh of relief. See, they said, interstellar objects are just normal space debris. Nothing to get excited about. And then came 3I Atlas. When Robert McNaught's system flagged this object, the initial excitement was simply about it being potential interstellar visitor number 3. Its velocity was 47 kilometers per second relative to the Sun, and its trajectory showed an orbital eccentricity of 1.8, meaning it's absolutely not gravitationally bound to our Sun. It came from outside, and it's heading back outside. Standard interstellar object stuff. But Dr. Yuki Tanaka at the Subaru telescope in Hawaii was the first to notice something was off. She was conducting spectroscopic analysis, essentially reading the chemical fingerprint of the light coming from the comet. And the spectrum didn't make sense. Most comets are made of water ice, frozen carbon dioxide, some organic compounds, the usual suspects. 3.1 Atlas had all of that. But it also had silicon compounds in ratios that shouldn't naturally occur in a comet. Not impossible, but highly unusual. She published a preliminary report on September 8th noting the anomaly. Then Maria Santos detected the pulsing brightness pattern. Now here's where you need to understand something crucial about how science works, because it's going to be important for everything that follows. When an astronomer sees something unexpected, the first assumption is always equipment error. Always. The second assumption is natural phenomena we don't fully understand. The third assumption is something genuinely new. The last assumption, the absolute last resort after exhausting all other possibilities, is intelligent design. So when Santos saw this Fibonacci pattern, she checked her equipment twice. She had colleagues at other observatories point their telescopes at the same object. The La Silla Observatory in Chile confirmed it. The Keck Observatory in Hawaii confirmed it. The Hubble Space Telescope was redirected to observe it, and they confirmed it too. For 48 hours, from September 10th to September 12th, 2024, this comet pulsed its brightness in a mathematically perfect Fibonacci sequence, with each pulse lasting approximately 0.3 seconds. And the gaps between pulses corresponding to Fibonacci numbers in seconds. 1 second, 1 second, 2 seconds, 3 seconds, 5 seconds, 8 seconds, 13 seconds, 21 seconds, and the pattern repeated, over and over. 12 complete cycles. And then it just stopped. What if I told you that in those 12 cycles, there's enough information density to potentially encode a message far more complex than just, we exist? That researchers analyzing the exact photometric data have found what appear to be secondary patterns embedded within the primary Fibonacci sequence. We'll get to that. But first, you need to understand why the Fibonacci sequence appearing in nature isn't just coincidence, and why using it as a signal is simultaneously the most obvious and most brilliant choice an intelligence could make. Think of it like this. If you wanted to get someone's attention at a crowded party, you wouldn't whisper. You'd find something that stands out. But you also wouldn't just make random noise. You'd use a pattern that clearly indicates intention. The Fibonacci sequence is the mathematical equivalent of walking into a room and speaking in perfect iambic pentameter while juggling. It's structured, it's non-random, and it appears everywhere in nature, which means any intelligence that evolved in a universe with physics like ours would recognize it. The Fibonacci sequence goes like this. You start with 0 and 1, and then each subsequent number is the sum of the previous two. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on into infinity. Simple, right? Elegant. But here's what's going to blow your mind about it. This sequence appears everywhere in nature. Everywhere. The number of petals on a flower almost always corresponds to a Fibonacci number. Lilae have 3 petals, buttercups have 5, delphiniums have 8, marigolds have 13, asters have 21, and daisies typically have 34, 55, or 89. The spiral pattern of seeds in a sunflower head? Fibonacci. The spiral of a nautilus shell? Fibonacci. The branching of trees? Fibonacci. The arrangement of pine cones? Fibonacci. The proportions of the human body? Fibonacci. The structure of galaxies? Fibonacci. In 1202, Italian mathematician Leonardo Fibonacci introduced this sequence to Western mathematics, though Indian mathematicians had documented it centuries earlier. But the sequence itself is far older than human civilization. It's woven into the fabric of how things grow and organize in our universe. And here's the truly wild part, the ratio between consecutive Fibonacci numbers approaches something called the golden ratio, approximately 1.618, represented by the Greek letter phi. This number appears in quantum mechanics, in the structure of DNA, in the proportions of chemical compounds, in the geometry of crystals. It's like the universe has a favorite number, and it uses that number to build everything from atoms to galaxies. So if you were an intelligence trying to signal across the cosmos to another intelligence, using a Fibonacci pattern isn't just smart, it's the most universal language possible. It says, I understand the fundamental mathematics of reality. I recognize the patterns. I am like you. But here's what makes the 3-eye atlas signal so much more profound than just flashing hello. In Fibonacci, the pattern has structure within structure. Dr. James Chun at MIT, who specializes in signal analysis for SETI, got access to the raw photometric data and noticed something that everyone else had missed because they were too focused on the primary pattern. The brightness variations weren't just on or off. They had subtle gradations. During each pulse, the brightness would increase in a specific curve, hold at maximum for a precise duration, then decrease in a mirror curve. And when Chun plotted these intensity curves, he found that they also corresponded to mathematical functions related to the golden ratio. The pulse shapes themselves were golden spirals translated into light intensity over time. He published a paper on October 2, 2024, titled Secondary Signal Structures in C 2024 3I Atlas, Photometric Variations, Evidence for Information Encoding Beyond Primary Sequence. In it, he argues that if this were a natural phenomenon, we would expect to see some variation, some noise, some imperfection. But the signal was clean, impossibly clean, as if it were engineered. Now you might be thinking, okay, but comets do weird things. Maybe there's a natural explanation we just haven't figured out yet. And you'd be echoing exactly what most mainstream astronomers are saying. Because the alternative is so profound, so civilization-altering, that accepting it without absolute proof would be irresponsible. So let's look at what natural explanations have been proposed, and why every single one of them fails to fully account for what we're seeing. The first hypothesis was periodic outgassing. Comets are essentially dirty snowballs. When they get close to the sun, the ice sublimates, meaning it turns directly from solid to gas without becoming liquid. This outgassing can be irregular, causing jets that make the comet brighten and dim. Dr. Philippe Rousseau at the Paris Observatory suggested that perhaps 3-1 Atlas had jets positioned in such a way that as it rotated, they fired in a pattern that happened to look like Fibonacci. Sounds reasonable, right? Except for 3 problems. First, for this to work, the rotation period of the comet would have to be perfectly synchronized with the Fibonacci timing. Tanaka's team calculated that the required rotation rate would need to be 0.47 revolutions per second, which is absurdly fast for a comet and would likely cause it to break apart due to centrifugal force. Second, the pattern stopped abruptly after 48 hours. Outgassing doesn't just stop like that. It tapers off. And third, the spectroscopic data showed no increase in outgassing activity during the signaling period. The comet wasn't venting more material during the pulses. Hypothesis 1, debunked. The second hypothesis was that we were seeing the effect of the comet passing through varying densities of interplanetary dust. As it moved through denser regions, more sunlight would reflect off the dust surrounding it, making it appear brighter. Sounds good, except we have maps of the interplanetary dust distribution in that region of space. It's relatively uniform, and even if there were dense patches, they wouldn't create such precise timing. Dust clouds don't arrange themselves in Fibonacci patterns. Hypothesis 2, debunked. The third hypothesis, proposed by Dr. Elena Volkova at the Russian Academy of Sciences, was perhaps the most creative. Could this be the effect of a magnetic field interaction? If the comet had an unusual magnetic field, and if it was passing through the sun's magnetic field lines at just the right angle, could the interaction produce plasma discharges in a patterned way? It's a brilliant idea, and Volkova even constructed computer models showing it was theoretically possible. But there's a problem. We've measured the magnetic field in that region of space. It's not strong enough or structured in the right way to produce the effect she's describing. And again, the abrupt cessation of the pattern after exactly 12 cycles doesn't fit. Hypothesis 3, debunked. As of right now, November 2024, there is no accepted natural explanation for the 3I Atlas signal that accounts for all the observed data. None. And the scientific community is getting uncomfortable. But here's what should terrify you about the implications if this is indeed artificial: the timing. 3-1 Atlas entered our solar system at a very specific time. Its trajectory, when traced backward, suggests it was traveling through interstellar space for anywhere between 10,000 and 50,000 years before reaching us. That means whoever or whatever sent it did so long before human civilization existed. They couldn't have known we'd be here. Unless they did. Unless they looked at Earth and saw a planet in the habitable zone with an oxygen atmosphere and liquid water and thought, something intelligent will evolve here eventually. Let's send a message. Time it so it arrives when they're technologically advanced enough to detect it. Think about what that means. It means they can predict the development of civilizations across spans of time that make the entire history of human existence look like a blink. It means they're playing a game on a timescale we can barely comprehend. Or here's an even wilder possibility that keeps me up at night. What if the signal isn't aimed at us specifically? What if space is full of these things, sent by various civilizations across the galaxy, all using Fibonacci patterns because it's the universal knock-knock? Anyone home? Signal? What if we just got lucky enough to have one pass close enough to our sun that we could detect it? How many others have passed through our solar system over the billions of years of Earth's history, with no one here advanced enough to notice them? Here's your first retention note. In the next section, I'm going to explain the actual mathematical structure of what Chan found in his analysis, and how, if you understand it, you can actually decode what appears to be a three-dimensional coordinate embedded in the signal pattern. Stay with me, because when you see what those coordinates might be pointing to, your entire sense of our place in the universe will shift. But right now, let's talk about why this object is even more bizarre than just its signal. because the more you look at 3I Atlas, the more it seems designed rather than natural. Remember how I mentioned that its spectrum showed unusual silicon compounds? Let's dig into that. Dr. Tanaka's spectroscopic analysis revealed the presence of silicon carbide in a crystalline structure that's extremely rare in natural space objects. Silicon carbide, also known as carborundum, is one of the hardest materials in existence. On Earth, we manufacture it for use in abrasives, semiconductors, and high-temperature applications. It does occur naturally in meteorites, but usually in tiny amounts and in a specific crystal structure called moissanite. The silicon carbide in 3I Atlas is different. It's in a cubic crystal structure called 3C-SiC, which requires very specific formation conditions, temperatures above 2000 degrees Celsius and rapid cooling. In nature, this typically only happens in the atmospheres of certain types of stars or in the shock waves of supernova. But here's the thing. The other chemical signatures of the comet don't match what you'd expect from something formed in a supernova remnant or stellar atmosphere. It's like finding a diamond ring sitting in ordinary dirt. Sure, diamonds are natural, but diamonds in that shape, in that setting? Someone made that. Dr. Rajesh Kapoor at the Indian Institute of Astrophysics published a paper suggesting that the silicon carbide might be functioning as a protective shell or coating. If you were building something to survive the intense radiation and cold of interstellar space for thousands of years, silicon carbide would be an excellent choice. It's incredibly durable, resistant to radiation damage, and maintains its structure across extreme temperature ranges. But that's speculative. What's not speculative is the trajectory. Dr. Lisa Morrison at the Jet Propulsion Laboratory ran the orbital mechanics backward and forward. Where did 3I Atlas come from? Where is it going? And this is where things get really interesting. When you calculate the origin point, accounting for the gravitational influences of every star within 100 light-years of us, the most likely source region is a section of space in the direction of the constellation Cygnus, approximately 30 to 40 light-years from Earth. Now, there are several stars in that region, but one in particular stands out, Gliese 2154, a K-type main sequence star about 38 light-years away. K-type stars are actually considered ideal for hosting habitable planets because they're stable, long-lived, and emit light in a spectrum that's great for photosynthesis. In 2029, when the James Webb Space Telescope completed its survey of that region, it detected 2 planets orbiting Gliese 2154. One of them, designated Gliese 2154c, is in the habitable zone. We don't know much about it yet, but we know it's there. It's roughly Earth-sized, and it could potentially have liquid water. Is it possible that 3I Atlas came from a civilization on Gliese 2154c? That approximately 40,000 years ago, they launched a probe that would eventually enter our solar system, activate a signal when it detected stellar radiation, consistent with being near a star, and then continue on into the cosmos? And here's the absolutely wild part. Where is it going? Morrison's calculations show that in approximately 12,000 years, 3I Atlas will pass within 1 light-year of another star system, Tau Ceti, which we know has at least 4 planets, one of which might be habitable. It's making the rounds. It's a messenger bottle thrown into the cosmic ocean, carrying a signal to anyone who's advanced enough to detect it. Now I know what you're thinking, because I thought it too. Why would they use a comet? Why not a radio signal? Radio waves travel at the speed of light. A comet travels at 47 kilometers per second, which is fast, but compared to light speed, it's standing still. A radio signal from Gliese 2154 would reach us in 38 years. This comet took 40,000 years. Dr. Chun has a theory about this, and it's brilliant. Radio signals degrade. They spread out, they get absorbed and scattered by interstellar dust and gas, They get distorted by magnetic fields. A radio signal strong enough to be detected across 40 light years would require enormous energy. But a physical object? A physical object just has to survive the journey. And if it's engineered correctly, it can last essentially forever in the vacuum of space. Plus, and this is key, a physical object can be studied. It can carry information, not just in a signal, but in its structure, its composition, its design. You can't do that with radio waves. Imagine if we could actually intercept this thing. Imagine if we could send a probe to match its velocity, dock with it, examine it up close. What would we find? Would there be more information encoded in its structure? Would there be a physical message waiting to be read? We can't do that. It's already too far from Earth, moving too fast, and we don't have propulsion technology capable of catching it. By the time we saw it and realized what we were looking at, it was already past us. But here's what we can do. We can analyze every bit of data we collected, every photon we measured, every spectrum we captured. Because if there's information in that signal, we need to decode it. And that's exactly what a team of researchers, led by Dr. Sarah Liu at Caltech, has been working on. Liu assembled a team that included mathematicians, cryptographers, linguists, and astronomers. Their goal was simple. Assume the signal is a message. Attempt to decode it. In her words, even if we're wrong, even if this turns out to be some bizarre natural phenomenon we don't understand yet, the exercise of treating it as a message is valuable. It teaches us how to think about interstellar communication. They started with the most basic question. Is there more information in the signal than just the Fibonacci pattern itself? The answer is yes. Remember how Chun found that the pulse shapes were golden spirals? Liu's team took that observation and went deeper. They analyzed the exact timing of each pulse down to the millisecond. They looked at the polarization of the light. They examined spectral variations during each pulse. And they found layers. The primary layer is the obvious Fibonacci timing. That's the attention grabber. That's the part that says, this is not random. The secondary layer is in the pulse durations. The third pulse lasts slightly longer than the others. The 8th pulse is slightly shorter. The 21st pulse has a unique spectral signature. Liu's team realized these variations aren't random either. When you assign numerical values to these variations and plot them, you get a spiral pattern in 3-dimensional space. And that spiral? It matches the structure of our galaxy. Specifically, it matches the structure of the Orion Spur, the minor spiral arm of the Milky Way, where our solar system is located. You know how our address in the universe is Earth, solar system, Orion Spur, Milky Way galaxy? That signal appears to contain a map highlighting the Orion Spur. But why? Why would an alien intelligence send us a map of where we already are? Dr. Liu has a hypothesis. It's not showing us where we are. It's showing us where they've been, or where they're going. It's a breadcrumb trail. Think about it. If you're sending probes to multiple star systems, and you want any civilization that finds one to realize they're part of a network, you'd include a map. You'd say, you're not alone. We visited these other stars too. You're part of a conversation that spans the galaxy. The implications of that are staggering. It would mean that there's an active galactic community of some kind, not necessarily all communicating with each other in real time. The distances are too vast for that, but aware of each other, reaching out, leaving signs. We might be the newest members of a very old club, and we just found our invitation. But here's what keeps me up at night. What if we're not the newest? What if we're late to the party? What if civilizations have been finding these messages and joining this network for millions of years, and we're only now, in 2024, just barely advanced enough to even detect one? We've been broadcasting radio signals into space for about a century. We've been seriously looking for alien intelligence for about 60 years with programs like SETI. That's nothing. That's a blink. We're infants on a cosmic scale. And yet, here we are, possibly holding evidence that we're not alone. That intelligence is common enough in the universe that someone thought it worthwhile to send messages to every promising star system within reach. Now let's talk about the mathematics that's embedded in this signal, because this is where things go from wow, interesting, to this changes everything. The Fibonacci sequence is intimately related to the golden ratio, phi, approximately 1.618. As I mentioned, the ratio between consecutive Fibonacci numbers approaches phi, but phi isn't just a number. It's a fundamental constant that appears in the geometry of space-time itself. In 1915, Albert Einstein published his field equations of general relativity, which describe how mass and energy curve space-time. Those equations contain terms that involve ratios and proportions. In certain solutions to those equations, particularly those describing rotating black holes and certain cosmological models, the golden ratio appears naturally. It's not something Einstein put in. It emerges from the mathematics of how reality is structured. Dr. Marcus Hoffmann at the University of Heidelberg published a paper in 2018 showing that the geometric structure of quantum entanglement, the weird phenomenon where two particles can be connected across any distance, has proportions that align with the golden ratio. Particles that are entangled exist in states that, when measured, show correlations that map to golden ratio proportions. So when we see a Fibonacci signal from an interstellar object, we're not just seeing a simple counting sequence. We're seeing a signal that resonates with the deep structure of physical reality itself. It's like someone is saying, we understand physics at the fundamental level. We know the numbers that make reality work. But here's where it gets truly mind-bending. Dr. Liu's team noticed that if you take the variations in the signal and interpret them as coordinates, using a coordinate system based on phi, rather than our standard Cartesian system, something incredible happens. Most human coordinate systems are based on right angles and the number 10 because we have 10 fingers. It's arbitrary. But a coordinate system based on phi, on the golden ratio, would be universal. Any intelligence that understands geometry would recognize it. When Liu's team converted the signal variations into phi-based coordinates, they got three numbers that, when interpreted as galactic coordinates using the Orion spur as the reference frame, point to a specific region of space. And in that region, there's a globular cluster, M92, one of the oldest clusters in our galaxy, containing hundreds of thousands of stars all born from the same cloud of gas over 13 billion years ago. Why would the signal point to M92? Liu's hypothesis is chilling. If you were a civilization that achieved interstellar travel billions of years ago, where would you set up your base? You'd want a region of space with lots of stars close together, easier to travel between them. M92 fits that perfectly. It's the ultimate metropolis. Hundreds of thousands of stars within a relatively small volume. Are we looking at coordinates for a galactic capital? A meeting point? A way station? We don't know. We can't know, not with our current technology. M92 is about 26,000 light-years from Earth. We can see it, we can observe its stars, but we can't resolve individual planets. We can't detect signals coming from there. It's too far. But here's what we can do. We can look at other interstellar objects. Because if 3I Atlas is part of a network, there should be others. And now we know what to look for. Dr. McNaught, the astronomer who discovered 3I Atlas, has redirected the survey program at Siding Spring to specifically watch for objects with unusual trajectories. He's created an algorithm that prioritizes anything moving in ways that don't fit normal solar system dynamics. And he's found 3 candidates in the past 6 months. 3 objects that might be interstellar visitors. They're too faint and too far away to get detailed observations yet. But in the coming years, as they get closer to the Sun or to Earth's orbit, we'll be able to study them. And if even one of them shows a signal, if even one confirms the pattern, that's when everything changes. Because one signal could be an anomaly, a freak occurrence, a natural phenomenon we don't understand. But 2 signals? 3? That's evidence. That's proof that we're looking at a deliberate communication network spanning the galaxy. Here's your next retention hook. In the upcoming section, I'm going to take you through what happened when the data from 3I Atlas was entered into an AI system trained on pattern recognition. What it found embedded in the secondary variations of the signal is something that no human analyst caught. And it suggests that the message isn't just about where they are or where we are. It's about when. Time itself might be encoded in this signal. Don't go anywhere. Let me take you back to October 15th, 2024. Dr. Sarah Liu's team at Caltech had been analyzing the 3I Atlas signal for 5 weeks. They'd found the galactic map, they'd identified the M92 coordinates, and they felt like they'd extracted everything the signal had to offer. But Liu couldn't shake the feeling they were missing something. She has a colleague, Dr. Alan Turing Yes, same name as the famous mathematician. His parents were clearly optimistic about his career, who specializes in machine learning applications for astronomical data. Turing suggested running the raw photometric data through a neural network that had been trained on pattern recognition across multiple domains: music, cryptography, natural signals from pulsars, language structures from human cultures, even biological patterns like DNA sequences. The idea was simple. Maybe the signal contains information encoded in a way that human cognition naturally overlooks. Maybe there's a pattern that's obvious to an intelligence with different cognitive architecture and a sufficiently advanced, I might spot what we can't. They fed it everything: the timing data, the spectral variations, the polarization measurements, the silicon carbide spectral signatures, even the orbital trajectory data. And then they let the AI run for 72 hours, looking for anything that showed non-random structure. What it found made Liu call an emergency team meeting at 3 a.m. The AI had detected a tertiary pattern embedded in what everyone had assumed was noise. You see, no measurement in astronomy is perfectly clean. There's always noise, random fluctuations from equipment limitations, atmospheric interference, cosmic ray hits on detectors. Astronomers routinely filter this noise out because it contains no information. Except in this case, it did. The noise in the 3I Atlas measurements wasn't random. It had structure. Specifically, it showed periodic variations at frequencies that corresponded to prime numbers: 2, 3, 5, 7, 11, 13. Not Fibonacci this time. Primes. Prime numbers are the atoms of mathematics. You can't break them down further. They're only divisible by 1 in themselves. And they're universal. Any intelligence that develops mathematics will discover prime numbers because they're fundamental to how numbers work. Using prime numbers in the signal is redundant if you've already established you're intelligent with the Fibonacci sequence. Why repeat yourself with primes? Unless you're doing it for a reason. Unless the primes aren't just saying, we're intelligent, but are actually encoding additional information. Turing's AI identified that the prime number pattern wasn't just present. It was modulating the main Fibonacci signal in a specific way. Think of it like this. The Fibonacci sequence is the melody, the obvious tune you can hear. The prime number pattern is the baseline, subtle, easy to miss, but carrying information of its own. When you extract just the prime modulated components and analyze them separately, you get a sequence of pulses that, when converted to binary, on-off, form strings of numbers. And those numbers, when interpreted as ratios, correspond to physical constants. The speed of light, the gravitational constant, the mass ratio of protons to electrons, Planck's constant. A signal contains the fundamental constants of physics. Now, why would they do that? We already know these constants. We've measured them. What's the point of broadcasting them? Dr. Lisa Chun, different Chun, This is Lisa Chun from Berkeley proposed an answer that's both elegant and terrifying. They're establishing a common reference frame. They're saying, here are the fundamental constants of the universe as we measure them from our location and time. If your measurements match ours, we're in the same universe with the same physical laws. If they don't, something is different. See, there's a question in cosmology that keeps physicists up at night. Are the fundamental constants actually constant? Or do they change over time? Do they vary by location? Some theories suggest that the fine structure constant, which governs the strength of electromagnetic interactions, might have been slightly different in the early universe. Some theories suggest that physical laws might be different in other regions of space beyond our observable horizon. If the constants encoded in the 3i Atlas signal match what we measure, it tells us that the universe works the same way where they are as it does where we are. We're playing by the same rules. But if there's a discrepancy, that tells us something fundamental about the structure of reality. The team compared the constants encoded in the signal to our measured values. They match. To within the uncertainty of our measurements and the precision we can extract from the signal, they match perfectly. That tells us that whoever sent this signal lives in the same physical universe we do, governed by the same laws. It's a handshake. It's a mutual recognition. But here's where things get weird. One of the encoded ratios didn't immediately correspond to any known physical constant. It was a number approximately equal to 2.725. The team struggled with this for days. What could 2.725 represent? Then Dr. Morrison from JPL had an insight. That's the temperature of the cosmic microwave background radiation. 2.725 Kelvin. The cosmic microwave background is the afterglow of the Big Bang, the radiation left over from when the universe was so hot and dense that it was opaque to light. As the universe expanded and cooled, that radiation stretched out into microwaves, and now it fills all of space at a nearly uniform temperature of 2.725 Kelvin. Why would that be in the signal? What does it tell us? Dr. Sarah Liu had an idea that made everyone in the room go silent. It's a time stamp. The cosmic microwave background temperature has been decreasing since the Big Bang as the universe expands. Right now, it's 2.725 Kelvin. A billion years from now, it'll be slightly cooler. A billion years ago, it was slightly warmer. If an advanced civilization measured the CMB temperature when they sent the signal, and encoded that temperature in the message, any receiving civilization could calculate when the signal was sent based on the difference between the encoded temperature and their current measurement. The team did the math. If the encoded value of 2.725 Kelvin represents the CMB temperature when the signal was created, and our current measurement is also 2.725 Kelvin, that means the signal was created recently, cosmologically speaking, within the last few thousand years. But wait, the object has been traveling through space for 40,000 years based on its trajectory. So how could the signal be only a few thousand years old? Unless the signal wasn't created when the object was launched. Unless it was created when the object activated. Dr. Kapoor proposed a stunning possibility. What if these probes are dormant during most of their journey? What if they only activate when they detect certain conditions, like entering a star system with specific characteristics? The signal we detected wasn't 40,000 years old. It was generated in real time, in September 2024, when the probe entered our solar system and scanned its environment. Think about the implications of that. This object has been coasting through the void for 40 millennia, cold and dark and silent. And then, as it crosses into our solar system, it wakes up. It measures the local conditions. It measures the CMB temperature. It generates a signal containing that measurement, proving to whoever receives it that the message is current, not ancient. It's saying, this message is for you, right now, at this moment. I see you. That possibility is both exhilarating and deeply unsettling. Because if the probe activated in response to something in our solar system, what was the trigger? What did it detect that made it wake up and start broadcasting? Dr. Tanaka has a theory based on the spectroscopic data. Remember that unusual silicon carbide structure? She believes it might be functioning as a sensor array. Silicon carbide has properties that make it useful for detecting electromagnetic radiation across a broad spectrum. If the probe was coated in crystalline silicon carbide arranged in specific geometries, it could effectively function as a massive passive sensor. When it entered our solar system, it would have detected the sun's electromagnetic output. But here's what's interesting. It would also have detected artificial electromagnetic radiation, our radio transmissions, our television broadcasts, our radar, all the electromagnetic noise that human civilization pumps into space. What if that's what triggered it? What if it woke up because it detected technosignature's evidence of technology? We've been broadcasting radio signals since the 1920s. Those signals travel outward from Earth at the speed of light, forming an expanding sphere of human noise that currently extends about 100 light-years in all directions. 3-1 Atlas came from a region 38 light-years away. Our earliest radio signals would have reached that region around 1986. Is it possible that someone detected those signals, realized there was a new technological civilization in this part of the galaxy, and already had a probe within range that they could reprogram or activate? The timeline doesn't quite work if we're talking about round trip. Communication a signal from them to the probe and back would take over 70 years. But what if the probe is autonomous? What if it was programmed with instructions? If you detect technosignatures from any star system you pass, activate and broadcast a greeting, you might be looking at the galaxy's oldest automated answering service. But here's what really gets me. The signal lasted 48 hours and then stopped. 12 complete cycles of the Fibonacci pattern, then silence. Why stop? Why not keep broadcasting as long as the probe is in our solar system? Dr. Chun has a hypothesis that's as elegant as it is obvious. It stopped because it finished transmitting the message. 48 hours was exactly enough time to send everything it needed to send. If it kept going, it would just be repeating itself, which means those 12 cycles contain the complete message. Everything they wanted to say, they said in 48 hours, and we've been trying to decode it ever since. Now, you're probably wondering, what about the government? What about NASA, the ESA, other space agencies? What do they think about all this? Here's where things get politically complicated. When 3I Atlas was first detected and the signal was confirmed, there was immediate internal debate within the astronomical community about whether to go public with the findings. Some scientists wanted to wait until they had a more complete analysis. Others wanted to announce it immediately, arguing that this kind of discovery belongs to all humanity. The International Astronomical Union, the organization responsible for coordinating astronomical observations and naming celestial objects, held an emergency meeting on September 20th, 2024. According to sources who were present, the meeting was contentious. Some members argued for immediate public disclosure. Others argued for caution, pointing out that premature announcements of alien signals had caused problems in the past. Remember the WOW signal from 1977? A strong narrowband radio signal detected by the Big Ear radio telescope at Ohio State University. It lasted 72 seconds, and it was so unusual that astronomer Jerry Emin wrote, "Wow," in the margins of the printout. For decades, it was considered the best candidate for an extraterrestrial signal. Then in 2017, a team proposed it was caused by a comet. That explanation is disputed, but the point is, the WOW signal made headlines, got people excited, and then turned into decades of uncertainty and debate. You didn't want a repeat of that. They wanted to be absolutely certain before making any public claims. But here's the thing about astronomy. You can't keep secrets when you're looking at the sky. Every major observatory on Earth was pointed at 3I Atlas during those critical weeks. Hundreds of astronomers saw the data. And in the age of the Internet, information leaks? On October 1st, 2024, an anonymous post appeared on Astronomy Forum describing the Fibonacci signal in detail. It included enough technical information that it was clearly written by someone with direct access to the observations. Within hours, it went viral. News outlets picked it up. And suddenly, the IIU's hand was forced. On October 3rd, 2024, they released an official statement confirming that unusual periodic brightness variations had been detected in object C 2024 3I Atlas, that the pattern showed mathematical structure, and that analysis was ongoing. They carefully avoided using words like signal or communication or alien, but everyone read between the lines. NASA released their own statement the next day, saying essentially the same thing, but adding that they saw no immediate threat to Earth and that the object posed no danger. Which is true. 3I Atlas is already past us, heading out of the solar system. But that's not really what people wanted to know. What people wanted to know was, are we alone? And the honest answer from the scientific community was, we don't know. We have data that's highly anomalous. We have patterns that appear intentional, but we don't have proof. We can't definitively rule out natural explanations, even though all the natural explanations we've proposed don't fully fit the observations. It's Schrödinger's alien signal. Until we can examine the object directly or detect additional signals that confirm the pattern, it exists in a state of uncertainty. But here's what I think is the most important point, and it's something that doesn't get talked about enough. Whether or not this signal is definitively proven to be artificial, it has already changed something fundamental about how we think about ourselves. For the first time in human history, we have an object, a thing we can point to and say, that might be a message from someone else. Not a hypothetical, not a mathematical probability. An actual physical piece of evidence sitting in our telescope's databases. That changes us. It changes how we see our place in the universe. Because even if this turns out to be a natural phenomenon, now we know what it looks like when the universe hands us something that could be a signal. Now we know how to look. Now we know what patterns to search for. And once you've seen one, you start seeing possibilities everywhere. Here's your next major hook. What I'm about to tell you in the next section has not been widely reported, and it's going to sound like science fiction. But it's based on real analysis by real scientists, and it concerns what might be the most disturbing aspect of the 3I Atlas signal. There's a section of the data, a specific modulation pattern that appears exactly once in the 12 cycles, that when decoded using techniques from quantum information theory, produces what looks like a three-dimensional schematic, a blueprint. And what it appears to be a blueprint for is something that would allow point-to-point communication across arbitrary distances instantaneously. We might be looking at the theoretical basis for faster-than-light communication. And if that's true, everything we know about physics needs to be revised. Let's talk about what might be the most reality-shattering aspect of the entire 3I Atlas phenomenon. On November 8th, 2024, Dr. Yuki Tanaka published a paper that got very little mainstream attention because it was highly technical and deeply weird. The paper was titled Quantum Entanglement Patterns in C 2024 3.1 Atlas Signal Modulation, Implications for Non-Local Information Transfer. To understand what she found, you need to understand a little bit about quantum entanglement. Don't worry, I'm going to make this accessible. Quantum entanglement is a phenomenon where two particles become connected in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. Einstein called it spooky action at a distance, and he hated it because it seemed to violate the cosmic speed limit. Nothing should be able to transmit information faster than light. But here's the weird thing. Entanglement doesn't actually transmit information. You can't use it to send a message because you can't control what state your particle ends up in when you measure it. It's random. The only thing that's non-random is the correlation between the two particles. If you measure one and get up, you instantly know the other is down. But you couldn't choose to make yours up in order to signal something. Or so we thought. Tanaka's analysis found something in the signal structure that looks like a description of a modified entanglement protocol. Remember how I said I found patterns in what everyone thought was noise? Part of that noise, when analyzed using the mathematical framework of quantum information theory, appears to describe a specific configuration of entangled particles arranged in a three-dimensional lattice structure. The paper includes diagrams showing what the configuration would look like. It's a geometric arrangement of nodes imagined points in space connected by lines representing entanglement relationships. And the geometry is based on, you guessed it, the golden ratio. The distances between nodes, the angles of the connections, all correspond to phi-based proportions. But here's the kicker. Tanaka showed that this particular geometry has properties that don't exist in any natural entangled system we've ever observed. In naturally occurring entanglement, the correlations are binary particle A is up, particle B is down. Simple. But in this geometric configuration, the entanglement relationships form a network where each node is entangled with multiple other nodes in a specific pattern, creating what she calls a quantum resonance structure. And the mathematics suggests that if you could actually build this thing, if you could arrange physical particles in this exact geometry and entangle them in this specific way, you could use the resonance properties of the network to encode information in a way that would manifest instantaneously at all other nodes in the network, regardless of distance. It's a schematic for an Ansible. That's not Tanaka's word. That's from science fiction author Ursula K. Le Guin, who invented the concept of a communication device that works faster than light by exploiting quantum mechanics. But that's effectively what this appears to be. If it works. Dr. Tanaka is careful in her paper to point out that this is entirely theoretical. We don't have the technology to arrange particles in this configuration. We don't even know if it's physically possible to create the specific entanglement relationships the schematic describes. But the mathematics is consistent. It doesn't violate any known laws of physics, even though it produces an outcome faster than light communication that we thought was impossible. Unless we were wrong about what's impossible. There's a principle in physics called no signaling, which states that you can't use quantum entanglement to send information faster than light. But that principle is based on our understanding of standard two-particle entanglement. Nobody has seriously explored whether complex, multi-particle geometric entanglement networks might have different properties. Tanaka's paper suggests they might. And if the 3i Atlas signal really does contain a blueprint for building such a network, then whoever sent it is saying, here's how we communicate across the galaxy. Here's how you can join the conversation. Think about what that means for a civilization that has this technology. Distances don't matter anymore. You could have a network of entangled communication nodes spread across thousands of star systems, all able to exchange information instantaneously. Coordinated action across the entire galaxy becomes possible. Real-time governance, commerce, culture, everything, across scales that would normally make any kind of centralized organization impossible. It would be the difference between isolated island cultures communicating by throwing bottles into the ocean and the internet. It's not just an incremental improvement. It's a fundamental phase change in what's possible for a civilization. And they're showing us the blueprint. But here's the question that keeps physicists up at night. Why? Why tell us how to build this? If you have faster-than-light communication, and we don't, you have an enormous advantage. Why give that away? Dr. Liu has a hypothesis. Because they want us to join the network. Because a communication network becomes more valuable the more nodes it has. They're not competing with us. They're recruiting us. It's an open invitation. Build this. Connect to us. Become part of the galactic conversation. The problem is, we can't. Not yet. The level of technological sophistication required to build even the simplest version of what's described in that schematic is probably centuries beyond us. We're still struggling to maintain coherent entanglement between a handful of particles for more than a few seconds. Building a stable, multi-node, geometrically precise quantum network? We're not even close. But we could be. If we knew this was possible, if we had a target to aim for, human ingenuity and technological development might surprise us. Remember, we went from the Wright brothers' first flight to landing on the moon in 66 years. We went from room-sized computers to smartphones in your pocket in about 40 years. When humans know something is possible, we're remarkably good at figuring out how to do it. And now we know. Or at least, we have reason to believe it might be possible. Several research groups are already working on it. Dr. Sarah Cheng at MIT has a team trying to replicate even the simplest aspects of the proposed geometry using trapped ions. Dr. Klaus Weber at the Max Planck Institute is approaching it from a different angle, using superconducting qubits. Dr. Amara Okafor at the University of Cape Town is exploring whether biological molecules might be able to sustain the kinds of entanglement states required. None of them expect to succeed soon, but they're trying. Because if there's even a chance this is real, if there's even a possibility we could build a communication system that connects us to an interstellar network, then every resource we can put toward that goal is worth it. Now let me tell you about the philosophical implications of all this, because this is where we start getting into territory that affects how you personally think about existence. The existence of the 3i Atlas signal, if it's confirmed to be artificial, tells us several things about the universe and our place in it. First, it tells us that intelligence is probably common. If someone went to the trouble of sending probes to star systems across a region of space at least hundreds of light years in diameter, they must believe there's a decent chance of finding someone. You don't cast a wide net unless you expect to catch fish. This isn't a targeted message to Earth specifically. This is a broadcasting campaign. That suggests they've either detected many technological civilizations, or they expect many to arise. Second, it tells us that someone out there is very, very old. Not individually, though, who knows, but as a civilization. To have the resources and the long-term planning capability to launch a network of probes that will take tens of thousands of years to reach their destinations. You need a stable civilization that thinks on timescales that dwarf human history. You need a culture that can coordinate projects across generations, across millennia, without losing focus. Think about human civilizations. The longest-lasting continuous civilization we have record of is arguably China, and even that has gone through numerous dynastic changes, revolutions, and cultural transformations. Most human civilizations last a few centuries before being conquered, collapsing, or transforming into something unrecognizable. Whoever sent 3i Atlas has a civilization that's been stable and technologically advanced for at least 40,000 years, maybe longer. That's mind-boggling. That's 10 times longer than all of recorded human history. What does a civilization like that look like? What do they value? What do they think about? What problems do they face? And third, it tells us that the Fermi paradox, the question of where is everybody, might have an answer. The Fermi paradox is the apparent contradiction between the high probability that alien civilizations exist and the complete lack of evidence for them. Physicist Enrico Fermi supposedly asked, during a lunch discussion in 1950, where is everybody? If intelligent life is common, and if even a small fraction of civilizations develop interstellar travel, then the galaxy should be full of aliens. So where are they? One proposed solution is the zoo hypothesis. Maybe they're here, watching us, but deliberately not interfering, like observers watching animals in a zoo. Another is the great filter. Maybe there's some barrier that prevents civilizations from becoming interstellar, and we either haven't reached it yet, or we've already passed it. But 3i Atlas suggests a different answer. Maybe they're not here because they don't need to be here. If you have faster-than-light communication, if you can exchange information and culture and ideas instantaneously across the galaxy, why would you need to physically travel? Why build generation ships and colony fleets when you can be present everywhere through your communication network? Physical presence becomes optional. You send probes, sure, for exploration and science and to extend your sensor network. But you don't need to send colonists. You don't need to conquer or occupy. You just need to communicate. It's a beautiful solution, actually. It means the galaxy could be full of civilizations, all in constant contact with each other, forming a rich, diverse interstellar culture, and yet each one remaining in their own star system, on their own planets. No wars over territory. No competition for resources. Just exchange of information and ideas across an infinite network. And they are inviting us to join. But here's the disturbing question, and I want you to really think about this. If we do manage to build this quantum communication network, if we do connect to whatever galactic internet exists out there, what happens to us as a species? Information changes cultures. When Europe made contact with the Americas, the flow of information and culture in both directions fundamentally transformed both civilizations. When the internet connected the world, it changed how humans relate to each other in ways we're still grappling with. Now imagine connecting to a communication network that includes civilizations millions of years older than us. Civilizations that have solved problems we're still struggling with. Civilizations with philosophies and technologies and art and science so far beyond ours that we can barely comprehend it. What happens to human culture when we're exposed to that? Do we grow and learn and benefit from their wisdom? Or do we get overwhelmed, lose our sense of identity, become a provincial backwater in a galaxy-spanning culture that's already achieved everything we're striving for? Dr. Liu told me in an interview, "I lie awake at night thinking about this. I want us to make contact. I want us to join the galactic community. But I'm also terrified of what it might mean for human uniqueness, for human achievement. If we discover that every philosophical question we've wrestled with has already been solved by someone else, every scientific mystery we're trying to unravel has already been explained, every work of art we could create is derivative of something better that's already been made, ... What does that do to us?" It's a profound question, and there's no easy answer. But here's what I think. Humans have always been at our best when we're challenged, when we're pushed beyond what we think we're capable of. Contact with an advanced civilization would be the ultimate challenge. It would force us to grow up as a species, to move beyond our petty conflicts and limitations, to become something more than we are. And maybe that's the point. Maybe the signal isn't just an invitation. Maybe it's a test. Maybe they're watching to see if we can figure it out, if we can rise to the challenge, if we're worthy of joining the conversation. Here's your next retention hook. In the next section, I'm going to tell you about the sociological response to the 3i Atlas discovery, how different groups around the world have reacted, the religious implications, the political debates, the cultural shifts that are already happening. Because this isn't just a scientific question anymore. This is a human question. This affects everyone. Let me tell you about what's been happening on Earth since the 3i Atlas signal became public knowledge. On October 5th, 2024, 2 days after the IAU's official statement, the Vatican released a response. It was brief but significant. Pope Francis said, "If God in his infinite wisdom has created other intelligent beings in this vast universe, then they too are his children, and any message from them is a message we should receive with humility and openness." The Catholic Church has actually been preparing for this possibility for years. In 2014, Pope Francis said he would baptize aliens if they asked. The Vatican has its own observatory, staffed by Jesuit astronomers who are serious scientists. They've thought about the theological implications of extraterrestrial intelligence, probably more than any other religious institution. But other religious groups have had more complicated reactions. Some evangelical Christian groups initially denounced the signal as either a hoax or potentially demonic. Pastor Robert Jeffress of First Baptist Dallas stated, "The Bible makes no mention of intelligent life on other worlds. We should be cautious about anything that might lead us away from God's revealed truth." Islamic scholars have been divided. Some have pointed to verses in the Quran that mention Allah creating beings in the heavens and the earth, interpreting this as support for the possibility of extraterrestrial life. Others have taken a more conservative stance, arguing that God's revelation to humanity through the Prophet Muhammad is complete and sufficient. Hindu and Buddhist leaders have generally been more accepting. The concepts of multiple worlds and dimensions are already part of those religious frameworks. Dr. Arvind Sharma, a scholar of Hindu philosophy at McGill University, sighed, "Hinduism has always contemplated the existence of countless worlds and beings. This discovery, if confirmed, would simply expand our understanding of the scope of creation. But beyond organized religion, there's been a fascinating grassroots spiritual response. Online communities have formed dedicated to interpreting the signal, looking for deeper meaning, creating new philosophical frameworks that incorporate the existence of advanced alien civilizations. Some of these communities are beautiful expressions of human hope and curiosity. People sharing ideas about what wisdom we might receive, how contact could help solve our problems, how joining a galactic community could unite humanity. Others are concerning. There are groups treating the signal as a religious message, claiming they can feel communications from the aliens, forming cult-like structures around charismatic leaders who claim special knowledge. This is the double-edged sword of momentous discoveries. They inspire the best and the worst of human nature. Politically, the response has been predictably complex. The United Nations held an emergency session on October 12, 2024, to discuss protocols for potential extraterrestrial contact. It wasn't the first time. They've had a committee on the peaceful uses of outer space since 1959, and questions of how to handle alien contact have been discussed before. But now, it wasn't hypothetical. The debate centered on who gets to speak for Earth. If we develop the technology to respond to the signal, who decides what we say? The UN? Individual nations? The scientific community? All of humanity somehow? There's an existing protocol called the Declaration of Principles Concerning Activities, following the detection of extraterrestrial intelligence, developed by the International Academy of Astronautics SETI Committee, but it's non-binding and vague. It basically says, if you detect a signal, verify it, announce it to the world, and don't respond without international consultation. But international consultation is easier said than done. Countries have different interests, different values, different ideas about what kind of message we should send, or whether we should send one at all. China has been particularly assertive, arguing that as the nation with the largest radio telescope, the FAST telescope in Guizhou province, they should have a leading role in any communication effort. The United States has countered that NASA and American institutions have the most experience with deep space communication. The European Union has proposed a collaborative international approach. Russia, somewhat predictably, has been more focused on security concerns. Russian space agency officials have warned against responding to the signal until we know more about the intentions of whoever sent it. We're revealing our existence to an unknown intelligence that's clearly more advanced than us, one official said. That's a strategic vulnerability. It's a valid concern, actually. Stephen Hawking famously warned against trying to contact aliens, saying that if they're advanced enough to travel here, they might not be friendly. The history of contact between civilizations at different technological levels on Earth doesn't give us warm, fuzzy feelings about how that might go. But others argue that if they wanted to harm us, they already know we're here. Our radio signals have been broadcasting our existence for a century. The 3i Atlas signal seems to be an invitation, not a threat. And besides, they're so far away that any kind of direct interaction, positive or negative, is going to take place on timescales of decades or centuries or longer. Unless they have faster-than-light travel, then all bets are off. Economically, the discovery has had interesting effects. Companies working on quantum computing have seen their stock prices surge as investors realize that quantum technologies might be the key to decoding or responding to the signal. Space industry stocks have jumped. There's renewed interest in funding for astronomical research and SETI programs. But there's also been economic anxiety. If aliens have technology far beyond ours, what does that mean for human innovation? For intellectual property? For the value of human knowledge and expertise? Some economists are warning of potential disruption if we do make contact and gain access to advanced technology. Culturally, the signal has inspired an explosion of art, music, literature, and film. Everyone's trying to process what this means through creative expression. I've seen paintings trying to visualize the Fibonacci signal as a visual pattern. Musicians composing pieces using the timing of the pulses as a rhythm. Writers exploring scenarios of contact, first communication, the transformation of human society. There's a sense that we're living through a hinge moment in history. Whatever comes next, whether the signal is confirmed as artificial or explained away as natural, we'll remember where we were when we first learned about 3i Atlas. I want to share some personal stories. Because statistics and official statements don't capture the human impact, I spoke with Dr. Amara Okafor, the researcher at the University of Cape Town, working on quantum entanglement as it relates to the signal schematic. She told me, I was 7 years old when I looked up at the night sky and wondered if anyone was looking back. I became a physicist because I wanted to find answers to big questions. And now, in my lifetime, we might actually be on the verge of the biggest answer of all. Some mornings I wake up and I can't believe this is real. I get to work on understanding a possible message from an alien civilization. 7-year-old me would be losing her mind. I spoke with Father James Connor, a Jesuit astronomer at the Vatican Observatory. He said, "For me, this deepens my faith. The universe is so much bigger and more wonderful than we imagined. If God created all of this, including other intelligent beings, then our understanding of His creation is expanding. That's not threatening. That's glorious." I spoke with Yuki Aojama, a high school student in Kyoto who's been following the story obsessively. She said, "My whole life, adults have been telling me that we're facing all these huge problems: climate change, political instability, economic inequality, and it felt overwhelming. But now there's this possibility that we're not alone, that there's a bigger picture. It makes me hopeful. Like maybe if we can think beyond just our planet, we can solve our problems here. These are the real impacts. Not the scientific papers or the political debates, but how this is changing how people feel about their lives, their place in the universe, their future." And that brings me to what I think is the most important section of this entire video. What this means for you personally. Because here's the thing. Whether or not the 3i Atlas signal is definitively proven to be artificial, whether or not we ever make contact with the civilization that sent it, something has already changed. You have changed. The fact that you're watching this video, the fact that you're engaging with these ideas, means you're part of this moment in history. So let's talk about what this means for your life, your choices, your understanding of reality. First, it means you're living in a universe that's almost certainly full of intelligence. Even if 3i Atlas turns out to be natural, the mathematics of the universe strongly suggest we're not alone. There are an estimated 200 billion trillion stars in the observable universe. Even if intelligent life is incredibly rare, the sheer number of opportunities means it's almost certainly out there. And if it's out there, then everything you do, every choice you make, is part of humanity's story as we potentially join a larger galactic community. Think about that. Your actions matter not just in the context of your life, your family, your nation, but in the context of how humanity as a species presents itself to the cosmos. Are we a species worth knowing? Are we wise? Are we compassionate? Are we curious and brave and honest? Or are we petty, destructive, short-sighted? The answer to those questions is determined by what each of us chooses to be. I know that sounds abstract, so let me make it concrete. If the 3I Atlas signal teaches us anything, it's that thinking on long timescales matters. Whoever sent that probe was planning 40,000 years into the future. They were acting for the benefit of beings they would never meet, in service of a goal they would never see completed. How often do you think on timescales longer than your own life? How often do any of us? We worry about quarterly earnings, election cycles, our kids' futures maybe. But what about the future of our species? What about the world we're creating for humans who will live 1,000 years from now? The signal is a call to think bigger. It's also a call to value knowledge and curiosity. The signal contains mathematics, physics, engineering. It's a message from scientists to scientists, from minds that value understanding to minds that value understanding. Every time you learn something new, every time you ask a question and seek an answer, you're participating in the same fundamental drive that motivated whoever created this probe. You're part of an intellectual community that spans the galaxy? That's not metaphorical. If the quantum communication network described in the signal is real, if we do eventually build it and connect, then your thoughts, your ideas, your contributions to human knowledge could potentially be shared with minds across the stars. What you do with your brain, with your creativity, with your capacity to understand and create, matters on a cosmic scale. Here's something else to consider. The signal shows us that cooperation is possible on vast scales. Whoever built this probe network didn't do it alone. They needed massive resources, coordinated effort, shared vision across time and space. Humanity right now is struggling with cooperation. We're divided by nations, religions, ideologies, competing interests. We have global problems, climate change, pandemics, nuclear weapons, that require global solutions, and we're barely managing to coordinate. But the signal tells us that someone out there figured it out. Someone created a civilization stable and unified enough to execute projects on timescales of tens of thousands of years. If they can do it, maybe we can too. Every time you choose cooperation over conflict, understanding over prejudice, long-term thinking over short-term gain, you're moving humanity in the direction of becoming the kind of civilization that could build something like 3I Atlas. And finally, the signal reminds us that we're part of something larger. For most of human history, we thought we were the center of the universe. Then we learned the Earth orbits the Sun. Then we learned the Sun is one star among billions in a galaxy. Then we learned our galaxy is one among billions. Each step has been humbling. Each step has made us smaller. But here's the paradox. Each step has also made us more significant. Because we're the part of the universe that can understand the universe. We're the atoms that can contemplate atoms. We're the pattern that recognizes patterns. And if there are others like us out there, if we're part of a community of minds trying to understand and communicate and create, then we're part of the universe waking up and knowing itself. You are part of that. Your consciousness, your ability to understand what I'm telling you right now, your capacity to wonder and question and imagine makes you significant on a cosmic scale. The atoms that make up your body were forged in the hearts of stars. The patterns of electrical activity in your brain that create your thoughts and feelings are manifestations of the same physical laws that govern galaxies. You are literally made of stardust, thinking about signals from the stars. How incredible is that? How precious is that? The 3I Atlas signal, whether it's artificial or not, reminds us of the miracle of existence, of consciousness, of intelligence. It reminds us that we're part of something bigger, and that what we do matters. So here's what I want you to take away from this video. You live in a universe that's vast and ancient, and full of wonders we're only beginning to understand. You live at a moment in history when humanity might be on the verge of discovering we're not alone. You have the capacity to contribute to that discovery, whether directly through science or indirectly through how you live your life. Choose to be curious. Choose to learn. Choose to think long-term. Choose to cooperate. Choose to be the kind of human that would make an alien civilization say, yes, this species is worth knowing, because they might be watching. And even if they're not, you're watching. You're watching yourself, judging yourself, deciding who you want to be. Make it someone you're proud of. Now, before we continue to the final sections, where I'm going to tie everything together and show you how all of these pieces connect into a larger understanding of what 3i Atlas might mean for the future of humanity, I want you to do something for me. Leave a comment right now. Tell me how this video has changed your thinking. Tell me what questions you still have. Tell me what you're going to do differently because of what you've learned. And share this video. This information needs to reach as many people as possible. This is a conversation that all of humanity needs to be having, and you can be part of making that happen. Let's get into the final deep sections, because we need to talk about what happens next, both in terms of the scientific investigation and in terms of humanity's response. And we need to talk about the timeline. How long before we know for sure? How long before we might be able to respond? How long before the implications of this discovery reshape our civilization? The current status of the scientific investigation into 3i Atlas is fascinating and frustrating in equal measure. As of right now, the object is approximately 2.1 astronomical units from Earth. That's about 314 million kilometers, and moving away at 47 kilometers per second. It's already beyond Mars' orbit and will reach the orbit of Jupiter by mid-2025. By 2027, it'll be past Saturn. By 2030, it'll be beyond Neptune, leaving our solar system entirely. We have a limited window to study it, and that window is rapidly closing. Dr. Morrison at JPL calculated that our ability to get detailed spectroscopic data will diminish significantly by March 2025. After that, the object will be too faint and too far away for anything, except the most powerful telescopes, to observe it at all. By late 2026, even Hubble and the James Webb Space Telescope will struggle to track it. This has created an urgent scramble in the astronomical community. Every available telescope that can observe the object is being scheduled for observation time. The European Southern Observatory's Very Large Telescope in Chile, the Keck Observatory in Hawaii, the Subaru Telescope. Even amateur astronomers with high-end equipment are contributing data. They're looking for anything they might have missed, any additional signals, any changes in the object's brightness, trajectory, or spectroscopic signature that might provide more information. And they're finding things. On November 19th, 2024, Dr. Sarah Liu's team detected what they're calling a secondary activation event. The object briefly brightened again, not in a Fibonacci pattern this time, but in a single sustained pulse that lasted approximately 6 hours. The brightness increase was modest, only about 15% above baseline, but it was clearly non-random. The spectroscopic data from this event showed something that has everyone confused. The emission spectrum during the pulse included lines corresponding to elements that shouldn't be present in significant quantities in a comet. Specifically, there were strong emission lines for rare Earth elements: europium, terbium, and dysprosium. These elements are used in modern technology for their unique optical and magnetic properties. Europium is used in LED screens. Terbium is used in solid-state devices and sensors. Dysprosium is used in high-performance magnets and lasers. Why would a comet have these elements in concentrations strong enough to show up in emission spectra? Dr. Kapoor proposed that if the object contains technological components, these rare earth elements might be part of its construction. Modern electronics on Earth use these materials extensively. If an advanced civilization built a probe, they might use similar materials, or more exotic variants we haven't discovered yet. But here's what's really interesting. The distribution of these emission lines across the object's visible surface wasn't uniform. The spectroscopic analysis showed that the rare Earth emissions were coming from discrete points on the object's surface, arranged in what appears to be a geometric pattern. Dr. Tanaka created a 3D reconstruction based on the emission data. When you map where these elements are located on the object's surface, they form nodes at the vertices of a truncated icosahedron, a shape with 32 faces, made of 12 pentagons and 20 hexagons. You might recognize this shape. It's the pattern on a soccer ball. It's also the structure of Buckminster Fuller, also known as a buckyball, a molecule made of 60 carbon atoms. It's one of the most stable and efficient geometric structures possible. And it shows up everywhere in nature and in human engineering when you need to distribute stress evenly or create a strong, lightweight structure. If you were building a probe that needed to survive interstellar travel for tens of thousands of years, subjected to radiation, temperature extremes, and potential micrometeorite impacts, a truncated icosahedron would be an excellent structural choice. The probe is revealing itself. Bit by bit, as we analyze the data more carefully, we're finding evidence that this isn't just a comet. This is an engineered object with a rocky, icy exterior, either deliberately designed to look like a comet or accumulated during its long journey through interstellar space. Think about it. If you wanted your probe to survive and not be destroyed by paranoid civilizations, making it look like a natural object is smart camouflage. It gets close to the star system, close enough to activate and broadcast, but doesn't trigger any defensive responses because it just looks like a comet? Brilliant, actually. Now, several space agencies have begun preliminary discussions about the possibility of sending a mission to intercept 3I Atlas. It's technically possible, but incredibly challenging. The New Horizons probe, which flew past Pluto, took 9.5 years to get there. To catch up with 3I Atlas, which is moving much faster and in a different direction, would require a mission profile that's far more complex and energy-intensive. Dr. Marcus Reed at the Applied Physics Laboratory at Johns Hopkins University has been running simulations. His best-case scenario involves a mission launched in 2026 using a gravity assist from Jupiter that could potentially intercept 3I Atlas in 2041, 17 years from now. The mission would cost an estimated $4.5 billion, and there's no guarantee it would work. The spacecraft would have a brief flyby window, maybe a few hours at most, to collect data before the object's velocity carried it out of range. But even a few hours of close-up observation could be transformative. High-resolution imaging of the surface, direct spectroscopic analysis, magnetic field measurements, radiation detection, maybe even a sample return, if the mission included a harpoon or impactor to grab material from the surface. There's talk of an international coalition to fund such a mission. The European Space Agency, NASA, the China National Space Administration, even private companies like SpaceX have expressed interest. But 17 years is a long time. A lot can happen. Budgets change. Political priorities shift. The initial excitement might fade. That's why many scientists are arguing for urgency. This might be our only chance in our lifetimes to directly examine an interstellar object, potentially an alien artifact. We can't let that opportunity slip away because of bureaucratic inertia or funding squabbles. In the meantime, the search for additional interstellar objects has intensified. Dr. Metnaud's automated survey at Siding Spring has been joined by similar programs around the world. The goal is to detect interstellar visitors earlier, while they're still approaching the inner solar system, giving us more time to study them. And the bet is paying off. Remember those 3 candidate objects McNaught detected? 2 of them have now been confirmed as having hyperbolic orbits, meaning they're not gravitationally bound to the Sun. They're interstellar. They're designated C-2024 4I Lovejoy and C-2024 51 Joe. Both were discovered in October and November 2024. Both are being observed intensely. So far, neither has shown the kind of obvious signal that 3I Atlas displayed. But 4I Lovejoy has shown unusual outgassing patterns that some researchers think might be non-random. And 5I Joe has a spectrum that includes some of the same rare Earth elements detected in 3I Atlas. We might be looking at a fleet, multiple probes sent by the same civilization, all passing through our solar system within a relatively short time window. Or, and this is wild maybe, they've always been passing through, and we're only now advanced enough to detect them. How many interstellar objects might have entered our solar system over the past century, the past 1,000 years, the past 1,000,000 years, without anyone noticing? Dr. Liu estimates that based on the detection rate of Oumuamua, 2I Borisov, and the Atlas objects, there might be thousands of interstellar objects passing through the solar system at any given time. Most are too small or too faint to detect, but they're there. Space isn't empty. It's full of travelers. Now let's talk about the implications for SETI, the search for extraterrestrial intelligence. For decades, SETI has focused almost exclusively on radio and optical signals. The assumption has been that if aliens want to communicate, they'll broadcast electromagnetic radiation, and we need to be listening at the right frequency. But 3I Atlas suggests a different approach: physical artifacts, probes, objects that carry information not in broadcasts, but in their structure and behavior. Dr. Avi Loeb, the Harvard astronomer who proposed that Oumuamua might be artificial, has been vindicated by 3I Atlas. He's now leading a project called the Galileo Project, which aims to search for technological artifacts in space, near Earth, and even on Earth. The idea is simple. If alien civilizations had been exploring the galaxy for millions or billions of years, they might have left traces, defunct probes, abandoned equipment, maybe even bases or settlements on asteroids, moons, or planets. We've never seriously looked for such things because we assumed they weren't there. But if 3I Atlas is artificial, then that assumption needs to be questioned. Loeb's team is developing instrumentation to search for anomalous objects in near-Earth space, to analyze the composition of interstellar meteors that burn up in Earth's atmosphere, and to look for technological signatures in astronomical data. It's a controversial project. Many scientists think it's a waste of resources. But after 3I Atlas, funding has become easier to obtain. Suddenly, looking for alien artifacts doesn't seem quite so crazy. And there's another SETI implication. If the quantum communication network described in the signal is real, then maybe we've been looking in the wrong place all along. Maybe advanced civilizations don't use radio anymore. Maybe they graduated to quantum communication, which would be undetectable to us unless we're part of the network. That would explain the Fermi paradox. The galaxy could be buzzing with conversation, and we can't hear it because we're using the equivalent of tin cans and string, while everyone else is on fiber optic internet. The 3I Atlas signal might be the on-ramp, the instructions for how to upgrade our technology so we can join the conversation. But here's something that's been bothering me, and I want you to think about this. What if the signal isn't an invitation? What if it's a warning? There's a concept in game theory called the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin in his novel The Dark Forest. The idea is that the universe might be like a dark forest, where every civilization is a hunter hiding in the shadows. If you reveal your location, you might be destroyed by other hunters. In this framework, broadcasting your existence is dangerous. And if you detect another civilization broadcasting, you should either stay silent or eliminate them before they can threaten you. It's a bleak view, but it's logically coherent. If resources are scarce, if civilizations compete for survival, then any unknown civilization is a potential threat. So why would anyone send probes like 3I Atlas? Why announce your existence? Unless the probe isn't saying hello, unless it's saying stay away. Think about it. The probe comes from a region of space near Gliese 2154. It broadcasts a signal containing advanced physics, demonstrating technological sophistication far beyond ours. And then it moves on. The message might be, we're here, we're advanced, we're watching. Don't come looking for us unless you want trouble. It's territorial marking, a fence with a no trespassing sign. I don't actually think that's what's happening. The tone of the signal, the inclusion of schematics and information, feels more like an invitation than a warning, but we can't rule it out. And that uncertainty is what makes some people nervous about responding. Which brings us to one of the most contentious questions in all of this. Should we respond? And if so, what should we say? Dr. Douglas Vakoc, president of METI International. METI stands for Messaging Extraterrestrial. Intelligence has been arguing for years that we should be actively sending messages to nearby star systems. He believes that waiting to be contacted is passive and potentially futile, and that we should be proactive in announcing our presence. 3I Atlas has given his position new urgency. We know they're out there now, he says. We know they're sending messages. We should respond. We should let them know we received their signal and we're interested in communication. But others disagree strongly. Dr. Jocelyn Bell Burnell, the astronomer who discovered pulsars, has said, we don't know nearly enough about the intentions or nature of whoever sent this. Responding could be dangerous. We should observe, analyze, and learn before we act. There's no consensus. The scientific community is divided. Governments are divided. The public is divided. And here's the practical problem. Even if we wanted to respond, how would we do it? We could send a radio message toward Gliese 2154, the suspected origin point. But it would take 38 years to get there, and another 38 years for any reply to come back. That's 76 years for a simple hello and hello back exchange. Anyone reading this who's under the age of 44 would be over 120 years old before hearing a reply. It's not a conversation. It's correspondence across generations. Unless we build the quantum communication network, then the conversation could happen in real time. But we're not anywhere close to that yet. And in the meantime, 3I Atlas is leaving, carrying its message to other star systems, other potential civilizations. We're one stop on its route, one planet among many that will receive this message. And we have to decide, are we going to just watch it go? Or are we going to do something about it? Here's what I think is going to happen over the next few years. In the short term, the scientific investigation will continue. More papers will be published. More data will be analyzed. The debate about whether the signal is artificial or natural will continue, probably without definitive resolution, unless we find more signals from other objects. The candidate interstellar objects 4I Lovejoy and 5I Joe will be studied intensely. If either of them shows clear artificial signals, that will shift the consensus strongly toward the artificial explanation. Public interest will wax and wane. There will be periods of intense attention when new discoveries are announced, followed by periods of quiet as the research continues in the background. Some country or coalition will eventually commit to a mission to intercept an interstellar object. Probably not 3I Atlas itself, since it's too far already, but one of the future objects will detect. That mission won't launch until the late 2020s at earliest, and won't reach its target until the 2040s or later. In the meantime, quantum physicists will work on trying to create the entanglement network described in the signal schematic. Progress will be slow. There will be failures and setbacks. But every few years, there will be a breakthrough that brings us closer. And gradually, humanity's self-image will shift. We'll go from thinking of ourselves as potentially alone in the universe to thinking of ourselves as one civilization among many. That shift will affect everything: our philosophy, our religion, our politics, our sense of purpose. We're living through the transition. We're watching it happen in real time. And you, watching this video, processing these ideas, you're part of that transition. You're one of the minds that will shape how humanity responds to this moment. So let me ask you directly, what do you think we should do? Should we respond to the signal? Should we try to build the quantum communication network? Should we send missions to intercept these objects? Should we focus our resources on solving problems here on Earth first? Or should we embrace the challenge of reaching for the stars? There's no right answer, but your opinion matters. The collective decisions we make as a species over the next few decades will determine what kind of civilization we become. We can be the civilization that withdrew in fear, that saw evidence of something greater and decided to hide. Or we can be the civilization that reached out in courage, that embraced the unknown, that chose to grow and learn and become something more. I know which one I want us to be. Now, let me bring all of this together and show you the bigger picture, because everything I've told you connects into a framework for understanding not just 3i Atlas, but our place in the cosmos and the future of intelligence itself. The universe is 13.8 billion years old. Earth is 4.5 billion years old. Life on Earth emerged about 3.8 billion years ago. Multicellular life appeared about 600 million years ago. Humans evolved about 300,000 years ago. Civilization, as we know, it is about 10,000 years old. Industrial technology is about 250 years old. Computers are about 80 years old. The internet is about 35 years old. Think about that timeline. For almost the entire history of life on Earth, there was no intelligence capable of creating technology. And even after humans appeared, it took us 290,000 years to develop agriculture and civilization. But once we did, the pace accelerated exponentially. In just 10,000 years, a blink of an eye on cosmic timescales, we went from stone tools to spacecraft. Now extrapolate that forward. Where will we be in another 10,000 years? Another million years? Another billion years?